Okay, why is that not working? There we go. So I'm going to take this fella, the f of t, between 2 and 5, and we're going to get its average value. So it's going to be 1 over b minus a, the integral from a to b. In this case, the variable is t. So it's going to be 1 over 3, because 5 take away 2 is 3. The integral from 2 to 5 of this ugly guy. So as I said, it looks like a u sub, and I'm convinced it is now. Put it over here. The u sub. Oh, well, that's the question. What is the u sub? Do you think I should use in this situation?
T squared.
Negative t squared.
Right. You can do t squared or minus t squared, whatever you feel like. I like t squared, so I'll use that one. Well, actually, I like negative t squared just to be different. If you differentiate it, you get that. Do the crossover. You get that. And then you isolate to get the dt. Now, the reason I changed my mind and did the negative t squared is just so that would become e to the u. And I just thought that might be a little bit less awkwardness for me. So it's going to be the integral of 5t e to the u and negative 1 over 2t du. And the t's cancel. And what I'm left with is the integral of 5 halves e to the u du. Question? That makes sense?
Yeah, that makes sense.
Almost forgot my negative, but caught it in time. What that's going to turn into is negative 5 over 2 e to the u, which then will become negative 5 over 2 e to the negative t squared. And now I can evaluate it at 2 and at 5. If you plug in 5, you get negative 5 over 2 e to the negative 25. Take away that becomes plus. And put in a 2, you get that guy. That's pretty much the end of that question. I guess I could tidy this up a little bit. I could pull out 5 halves, and that would get me 5/6. And I could put that one first and do it like that, and put this one second and do it like that. So that might look a little prettier, but that's about really all I could do.
Okay, thank you.
Right. Are we good?
Yeah.
Okay. I'll call that one done. It looks like still have a few people to turn up. I'm having technical difficulties, which means I pause a lot because I don't multitask. And when something happens, I have to focus on it, and then it kind of breaks up my thought process a little bit. Okay, 2, 4, 6, 8, 10, 12, 13. Where are the other 11 of you? That's the problem. We got about slightly more than half of the class here. Is there a party somewhere and we haven't been invited? Nope. What else could have happened? Has somebody won the lottery and invited a whole bunch of our students to Vegas?
I wish.
Yeah, well, you weren't invited, so too late. Neither was I. Okay. Of course, if I start the lesson, then people will turn up, right? I've got a couple more people just turned up as I spoke. Zarwin. Okay, everyone, good morning. My goal today is to do some questions from 6.4 to get that over with. We're going to basically only do two kinds of questions. I'm going to start with some more Hooke's Law questions, and then we're going to finish with some application questions where we're going to find out how much work is done in lifting objects up buildings. Evidently, engineers like finding that out. And then at the end, we'll talk a little bit about your test, which, as you already should know, is due on Tuesday. So let's start with an example of Hooke's Law. So suppose you are given a spring and its natural resting position, which is that basically is that distance. Let's suppose it's 2 meters. And we're told that it takes 20 units to extend it. Four meters beyond its natural length. And that is actually information. That's not really a question. What it does is it allows us to find what we call K, the constant for the spring. And then you have a question that might go something like this. Question A. How much work is done in stretching the spring? "150 centimeters beyond its natural length." So that's going to be my first question. Let's see how you set it up. According to Hooke's law, the force function, the force required to stretch a spring X units beyond its natural length. So if you imagine that's its natural length, what they did is they extended that spring another extra, in this case 4 meters. And according to Hooke's law then, the force, which is 20, is K times the distance beyond its natural length, in this case is 4, and that gets me the value of K, which now means that the force function is 5x. Now, if you know that, you can then answer this question. How much work is done in stretching the spring 150 centimeters beyond its natural length? I'll suppose I want to do that. It's going to be the integral of 5x dx. Well, it's going from 0 to 150 centimeters beyond its natural length. Do I put 150 as that top number? Correct. You don't. What number do I put there?
1.5.
So always be aware of units, because sometimes they do that to catch you out, right? Now, in this particular question then, a little wobbly line here, the work is going to be 5 halves x squared, evaluated from 0 to 1. It's going to be 5 halves 1.5 squared take away 0. And in this case, decimals are okay. So if I divide by 2 times 1.5 squared, and the answer is 5.625. We comfortable with that question? Okay. How about this question? Imagine there's a part B. How much force do you need to stretch the spring 2 meters beyond its natural length? Well, actually, this question is not that hard to do. You want to know how much force is required to stretch it 2 meters? Well, we know what the force function is. It's that guy. What does it take to stretch it 2 meters? Just simply 10 newtons. So we don't really need to integrate anything in that second example, isn't it? Basically, you've told me everything I need to know. You just want to know what the force would be at any given point. So if I want to stretch it 10 meters or 2 meters or 0.1 of a meter, it would simply just be 5 times that number for this spring. Are we okay with that one? Right. So I'm doing one more, but I'm going to do an awkward one where the information isn't quite the way you would want it to be. So there's my little spring. And in this case, the natural length of that spring is 40 centimeters. And they tell you it took 10 newtons to stretch it to 45 centimeters. And then the question is, how much work is done stretching the spring from 50 centimeters to 80 centimeters. That looks very similar to the typical Hooke's law question, and it's going to be done in a very similar way. And the main difference is units. Units and value. Units is pretty obvious. Everything needs to be meters. What do I mean by value? Well, let's show you. Isn't the force function that guy? And I know that's 10 newtons. And you might be tempted to just say, well, X here is just going to be, right, 45 centimeters turned into meters, which would be 0.45. But X is not 0.45. Isn't X how much you stretch it beyond its natural length? So this number here is now very important, because if you stretch it to 45 centimeters, haven't you really only stretched it an extra 5 centimeters? So the X here is the stretched, the extra stretching part. And 5 centimeters is now turned into a meter. So units, it's in meters, and now value. Now in this case, if you want to find out what K is, you divide both sides by 0.05. And let's see what that looks like. 10 divided by 0.05. And the answer I get is 200. So I now have the correct force function. Are you comfortable about that little sneaky way in which the information was given to you, rather than the typical way where they just tell you the stretch distance is 10 or whatever? Now the second part is actually answering the question, how much work is done? Well, I need to know where to start and where to finish. Well, they have a start value, bring this a little bit lower. They have a start value of 50 centimeters, and then you go from 50 to 80. Now, at the 50 centimeter mark, isn't the X value 10 centimeters? 10 centimeters beyond its stretch, right? You stretched an extra 10. And isn't this one, whoops, 40? So what you've done is you're going to be stretching it from an X value of 0.10 to an X value of 0.40. And that becomes 100x squared evaluated at those 2 points. What does that look like? It looks like 100 times 0.4 squared, take away 100 times 0.1 squared. That's 16, that's 1, so the answer is 15 joules. Okay. Any questions about that? Are we comfortable with the process? Some nods. I'll take that. Well, Hooke's law is pretty straightforward. A couple of kinks, but pretty straightforward. Now we're going to start looking at not at all straightforward. This one are going to involve quite a bit of thinking. So these are stories about lifting objects, mostly ropes, but sometimes buckets and other objects, up to the top of buildings. Right. So imagine I have a building, look like this. And this building is 200 feet tall. And on this building, we have a rope. So it's obviously 200 feet because the rope reaches the ground. What else am I going to tell you? Well, I'm going to tell you that the rope weighs half a pound per foot. So you're told the height of the building, you're told the length of the rope weighs half a pound a foot, and we are going to find the work done in getting the rope, all the rope, to the top. Well, you might just say, well, that's not that hard. 200 feet of rope, half a pound a foot, that means the entire rope weighs 100 pounds, right? That's it, you know, the whole rope, 100 pounds. And I'm going to take that 100 pound, I'm going to raise it 200 feet. And isn't the formula weight times distance, right? Force times distance. Great. But that's actually not what would happen. That calculation would be true if you had the whole rope as a big pile and you went to the bottom and you crawled up a ladder to the top. You would be carrying 100 pound of rope for the entire journey. But if you think about it, if you're at the top pulling that rope up, can you imagine what would happen if you were halfway? Won't you only be pulling up half the rope? Isn't that a lot less weight? And then at the top, you're only pulling up, what, 1 foot, half a pound. Can you see at the bottom, you're carrying a lot of rope, and at the top, there's virtually none. Do you see that as you move up the building, right, as you pull the rope up, doesn't the amount of rope get smaller, and therefore the work needed to pull it is less? So what that means is that we now have a harder question. We need to find the force function. And basically, the force function is going to be the weight of the rope at position. And we are going to call this fella position xi. So I want you to imagine that we randomly pick some point about here, right? And at this point here, we're calling that distance xi. So at that point, this is how much rope you'd be holding on to, right? This is how much rope you're about to pull. Now, how much does that rope weigh if you make this distance xi? Well, that's not too hard to calculate, because since the weight of the rope is half a pound, it's half of whatever the length of xi is. Would you agree that's the weight of that rope? If the rope weighed 5 pounds a foot, wouldn't that amount of rope weigh 5, whatever xi is in length? So this is our force function. Now, we need to think about moving it just a tiny little bit. So we'll do that. The book then goes into a Riemann sum, where you go I equals 1 to n, you do the limit as n tends to infinity, that's fixed. The work done is what you would have to do if you did all these tiny little movements from the bottom to the top. So you'd basically be doing that. So in these questions, there are typically 2 boxes. One of them is this funny sigma thing. And we kind of try to talk you through it, but essentially, you find the weight of the rope at position xi, and you stick a delta x at the end. Now, how does that help us actually answer the question? This thing turns into an integral. It basically turns into the force function. Now, we need a start and a finish number. Well, if the rope is 200 feet, won't you start at nothing and finish at 200? And what this does is then that is now allowing us to figure out or to incorporate the fact that the weight of the rope keeps changing as you move up the building with it. So all we need to do now is add 1 to the power, divide by the new power, evaluate it at 0 and at 200. And you get 10,000 joules. Now I can answer other questions now that I know the force function is a half x. Suppose I only did 0 to 100 of the force function. Suppose I did 100 to 200 of the force function. What work would I be calculating with these two? Well, I'll start with this one. I'm only going to find out the work from x equals 0 to 100. And this one, 100 to 200.
You would be finding the work for pulling the rope halfway up on each of those?
Yeah.
So you could compare those and ask which person had to do more work.
Yeah, I can tell you, wouldn't the guy who was pulling at the start doing more work than the guy that was pulling at the second half?
Yeah.
Right. But you see now how easy it is, because we have integration and calculus, to split an entire job into little bits. You know, hey, how come I get the job of pulling up the rope at the beginning and you get the job of finishing it? You know, I do
Similarly,
more work than you. You know, that kind of argument. But now you can actually put a number on it, can't you?
yeah, I guess you could probably also calculate exactly how much of the rope the first person would have to pull for it to be fair.
Yeah. And the way you would do that is you'd put a variable, let's call it C. And then you'd make these equal to each other and solve for C. So C would represent that magic sweet point where, you know, the work on the first one was the work on the second one. My gut feeling is, and it's just a gut feeling, that it's probably something like 2/3, 1/3 kind of split. You know, like the first 1/3 of the rope is a lot more work, or exactly the same amount of work perhaps as the second 2/3. But that's just a gut feeling. I think it depends on how tall the building is, and I think it also probably depends on how heavy the rope is, because I'm sure those numbers change. Yeah, I kind of like that question. I would have, they don't have a homework one like that, but they should have. Wouldn't that have been a really... You should talk to the guy that wrote this book. Send him a letter saying, hey, I've got a good idea for one of your questions. Yeah. That's a pity, because see, if I was working at school, right, physically, then I would be doing your test myself. I'm going to put note to self, make that a question, because I like it. I like the way your brain thinks. Okay, so, well, moved that far too quick, I've just realised. So, that's our first foray into pulling ropes up buildings, right? I'm going to do another one of those, but I'm going to make it just a little bit different. Each one's going to be a little bit different from the previous one, a little bit harder. So here's my building. Actually, it doesn't need to be a building. It can be a hole in the ground. It's the same question. This time, I'm going to change the height of the building. Not that that matters too much, but just so we're not using the same numbers. And it's 50 feet. Here's my little guy at the top. Here's this rope. But I'm going to give him a little bit extra work to do. This rope, right at the bottom, there's a bucket. And the bucket weighs 10 pounds. And the rope, well, I guess the rope is 2 pounds per foot. Now I'm going to tackle this question just a little bit differently, but only a little bit differently. I'm actually going to find the force function, then we can do this Riemann sum kind of after the event. So, can you imagine, where the heck am I going here? Can you imagine a kind of random point in the journey, say here? Only this time I'm just going to call it x rather than xi, because I'm going to go straight to the force function and then work backwards. Now, the force function at position x is made up of the weight of the rope plus the weight of the bucket. And so this is a little bit different, just a little. Isn't the bucket 10 pound at the start and it's still 10 pound at the end? It's a fixed number that ain't going anywhere. On the other hand, at position X, how much rope is that going to weigh? Well, X feet of rope, 2 pound. Are you happy about where my 2X came from? I've changed one piece of information, right? The rope now weighs 2 pound a foot. So X feet of rope, 2X is how much it's going to weigh. So that's my new function. So let's do the Riemann sum thing. You just get it out of the way. That's what it would look like as a Riemann sum. You see, all I'm doing is replacing this here and sticking the delta x. Now we can get the work done. It's from 0 to 50 this time of the force function dx. So that's going to be x squared plus 10x And that's going to be evaluated at 0 and at 50. And that's getting us 50 squared plus 10 lots of 50, take away nothing. 2,500 plus another 500, I make that 3,000. Oh, the units here would be foot-pounds. Are you beginning to get a feel for pulling things up buildings question? Right, now, couldn't I change that bucket to £20? It wouldn't really matter. Couldn't I make the rope wear more or less? Couldn't I say the rope was £5 a foot or £0.2 a foot? Couldn't I make the building 500 feet tall or 50 feet tall or 4 million feet tall? Isn't the structure of that question not really going to change much? All it's going to change is the numbers that get used in it. But the way that it was created, which is basically finding the force function, isn't that the key? You get this guy, the rest just comes out pretty straightforward.
I have a question.
Yes.
Would you be able to use a similar problem like this for calculating like the weight of, say, like a submarine going up water and with the water pressure and the weight of the submarine?
I'm trying to think. So that £10 would really just represent the submarine. The submarine's not changing its weight as it moves upwards. So that calculation would simply just be weight. Oh, no, no. It would change, but it'd be a different kind of calculation. If you think of a submarine,
buoyancy.
it's got its buoyancy, but if you think the way they think of a submarine is if it's lying on the ground, doesn't have a column of water above it.
Yeah.
And so when that moves upwards, won't that column of water change because there's less? So
Yeah.
I probably could create an equation that would do that, but it would be a little bit different because I'd need to know things like how much water weighs, what the surface area of the submarine is. And then there's all sorts of other things that the submarine can do just to change that calculation. Couldn't they blow their ballasts and have more air and less water so the submarine actually weighs less as it's moving up? So that could be changing as well. So is it possible? Yeah, if you give me enough information. And it would have a similar kind of feel to, well, essentially the main part would be to find this guy, right? The minute you know the force function, you integrate it over wherever it is to wherever it's going, and that would be the work done in doing that.
Wouldn't you also have to consider once the submarine gets off of the bottom, the pressure not only on top but also below it? So I guess that would be buoyancy.
Yeah.
So that would be like that would
believe
be force acting upwards, kind of.
what the water below it is pushing it upwards as the water above it is pushing it down. Is that what you're thinking?
Well, there's water pressure, yeah.
Yeah. There's a funny rule that I remember from somewhere that says that when you're in a submarine, the pressure on all sides, top, side, and bottom, is the same number.
Really?
Yeah. I don't know why that is, but you can look it up. So what you said kind of makes sense, but I don't think in the physics of it, it actually works. I don't know why. That in a submarine, the pressure underneath is exactly the same as the pressure above, even though there's less water. I think it must be a property of water. It's not, it's kind of, it wraps around the thing, so maybe that's what it does. Well, I get one more of these guys, and then after that I want to talk about the test. And I'm going to hit you with everything that can go wrong is going to go wrong with this question. In other words, I'm going to make it downright as ugly as theoretically possible. So here goes. I'm just going to stick to buildings again, so at least we've got a common theme. And this particular building is going to be 100 feet. Poor little guy at the top. Here's his rope. And here's a bucket. Everything's kind of looking the same. Oh, I changed my mind, sorry. I meant to do this. We'll make it 100 meters. I haven't done any metric yet, right? Here's your little rope. At the bottom, there's a bucket that weighs 10 kilograms. The rope is going to weigh half a kilogram per meter. Right, because it's metric, right? Everything's metric. And if that wasn't bad enough, inside this bucket, there is 20 kilograms of water. Well, you're thinking, no biggie, that just means the bucket weighs 30. Yeah, too easy. The water's going to leak out. And it's going to leak out so that it's empty when it reaches the top. So what you got here is a guy with a rope, a bucket of water. He's pulling this bucket of water to the top. As he's pulling it, water is gushing out of the bucket. And when he gets it to the top, the bucket is empty, to which he's probably annoyed at doing all that work and still didn't get any water out of it, right? It's one of those, this is actually a classic question, the empty bucket. So it's not just me inventing that, they've got questions and the homework just like it. And I've pretty much seen a version of this in every textbook since a way back when. So this is a problem. So let's show you how you're going to tackle it, because you're going to have to tackle it just a little bit differently. We are going to be counting the X value. Not from the top. X is going to represent how far off the ground you have got. So that's a slightly different notation. Have you noticed that before we always counted X in this direction, right? From the top to the bucket or whatever. Here, X is going to represent this distance, right? Now, the force function at this position X, well, the way I see it is made up of three things. Isn't it made up of a rope, a bucket, and the water? Agreed? Now, the only one of these that's the easy one is the bucket, because the bucket's 10 at the start and it's at 10 at the finish. Would you agree that everybody else changes as the bucket moves up? So let's figure out what the weight of the rope is. Well, it used to be dead easy. Didn't it used to just be a half times X? But that's what it was when you counted it this way. So now we have to figure out how much rope there is. Would you agree? Now, if you're X off the bottom and the building is 100 meters, doesn't that make the rope 100 take away X? Isn't that the length of rope that you've got in that position? X off the bottom, that means you've got 100 minus X of rope. So the rope is going to weigh 1/2 of that number. Are you happy where the 100 minus X came from and why it's times 1/2? Okay, now the harder one, I think, is figuring out the weight of the water. So I'm going to have to do a little calculation here. There's 20 kilograms of water and there's 100 meters. If you do a quick division, doesn't that mean that you basically use or lose 0.2 kilograms per meter? So every meter that you move, don't you lose 0.2 of a kilogram of water? Now, at position here, won't we be able to find out how much water you've lost? Well, you've lost 0.2x kilograms of water. I don't want to know how much water I've lost. Don't I want to know how much water I've still got? So how do I figure out what that is at position X? Well, don't I just say 20 kilograms, take away what I lost? I think out of the three, I think that's the hardest one to get your head around, but does that make sense what I did there? Now, all of this expression should be multiplied out in collect-like terms. So here we go. There's a 50. There's take away a half x. There's add a 10. There's add a 20. There's take away 0.2x. That guy, and that guy gets me 80. And I guess I should call that 0.5s to work with this guy. So negative 0.7x. Bingo. There's our guy. Now, how much work is done? Well, going from 0 to 100, force function, dx. Are we cool about that? Now, that becomes 80x, take away 0.2 over x squared, evaluated at 0 and 100. So that's 80 times 100. Take away 0.7 times 100 squared over 2, minus nothing. And what's that? 8,000. That guy there should be a bit messy, but let's see. 0.1 times 100 squared. And then you divide that by 2, you get 3,500. So and everything looks great, doesn't it? There is a problem here. What did I miss?
You only have the mass, you don't have the weight, because you're working with kilograms.
Yeah, and when we did it yesterday, didn't I say to you, when you do metric, don't you have to multiply everybody by?
9.8 meters per second.
Now, I can fix that, I'm glad to say. So 4,500 times 9.8, and now we have 44,100 joules, 44,100. So just when you think, you know, like the horror movie, just when you think you're safe, the monster pops out and it's still alive. You fight your way through this entire question and you get to there and you plug it into WebAssign and it says error. And your most likely reaction is, after you finish screaming, is, I thought I knew how to do this question, but I keep getting it wrong. That is a good example of a question, if it appears in your test, why showing me you're working is going to help. Because if you went through this entire process, but the only little piece you missed was the 9.8 times, instead of getting 0 out of 10, which is what WebAssign does because it only knows the right answer and it doesn't give partial credit, can you see that you probably get 8 or 9 out of 10 because you really did do the question properly, right? Just a little hiccup on units. Are we good? Right. I think I kept my promise. Would you agree that is the ugliest version of that question you could possibly get? Right? I mean, the only thing I could add to that question is that the guy at the top was yodeling, so how long did it take him to stop? Right? I mean, just throw in some weird question that makes no sense. That's pretty much everything that you could do to that shape, and it is done. So,
what if you gave the height of the box?
oh God, yeah, I guess you could add the height of the box, which would reduce the length of the rope by whatever the height of the box was. Yeah, that's a little adaptation you could do. You could have it so it has some water at the end instead of empty. I've
Oh,
never
you
seen
could use that.
adaptation.
You could use that water emptying from a tank formula, like if you knew the amount of water and like the size of the hole in the bucket.
Oh God! So the water doesn't even come out at a fixed rate; it comes out at a rate dependent on some other formula.
Yeah.
Yeah, I
Yep.
guess you could. I guess if you went crazy, you could really go to a point where it'd be a cool kind of project, you know. Try and do the bucket question in the ugliest form you can find. I just
Really
thought of
fun to-
something. Sorry, you were saying?
Oh, it'd be really fun to turn this into like a firefighting helicopter question somehow. You know how they do the scoops with the buckets and then drop it on forest fires?
Oh, yeah. I mean, how much work would it take to lift the, an empty bucket and collect it and lift it? Yeah.
Yeah, and then like you have a formula for how much fuel it would use, so you would need to know like how much fuel you would need to put out a certain size of fire.
Yeah, a lot of those type of applications where you simulate things are very often done on computer, mostly because the amount of math in them gets really messy, and we know how to do the math, but it's much easier just to get a computer to figure it out. I mean, you can use Mathematica today, and you can plug in the most ugliest looking things in the world, and it rattles off the answer. Before we move on to the test, and to get this thought out of my head. I just thought of the submarine raising in a slightly different version. If a submarine is incapacitated, they can actually get big cranes and lift the submarine out of the water.
Oh, interesting. Never
So
heard.
that question that we've been doing with pulling things upwards, that question could certainly be adapted to that situation, because at least the submarine is fixed. It's not changing anything as you move it. And so the question really just becomes a matter of what would the work done be needed to do that. And one of the reasons they need to know work done is you can only lift a submarine with a crane that's got enough power to lift the submarine, right? So you want to kind of know what the work done is, because won't that transfer into like horsepower kind of thing, and that in turn could turn into what kind of sized engine you would need to work the crane that would pull the thing up. Now you can avoid that a little bit. Can't you pull up the crane slowly, in which case you can get a weaker engine could do the job.
But if your submarine has a leak, then you'd have a time limit. And the submarine would get heavier as it goes on, wouldn't it?
We are not using you anymore. You're just making my easy question so much harder, Megan. You're going into the. They don't do this anymore. But don't they have? You're going to the corner. Remember in the classroom thing when you're really young, go to the corner.
Is there a computer in the corner?
No, Kathy. Were you at school when that was allowed?
No, but we did definitely have like you could definitely get sent to the office.
Okay.
Like the principal knew me.
Okay. I was, as you probably had expected, I was a really, really good student. And not talking academic, like I'm talking I just never got into trouble. I was not allowed to get into trouble, so I was trained really early not to. If you had 6 sisters, as I did, who were all older than you, you couldn't get away with anything. It was like the KGB were watching you. I mean, we had what we call a swing park across the road where I lived when I was really young. And this swing park was like heaven to me, but I wasn't allowed to go to it because you had to cross the main road when I was really young. And I would look around, and if I didn't think any of my sisters were doing it, I would try and go to the swing park. And 99 times out of 100, there was always one of them who saw me and shouted, and I had to stop. So anyway, at school I was very much never get into trouble. Secondly, if I ever did get into trouble, my dad would kill me when I got home. So that was an extra bonus to not literally kill me, but he certainly would. I'm I'm trying to think of how to describe this.
It would make you regret
Corporal
misbehaving.
punishment was still allowed in those days. How about phrase it that way? Okay, let's talk about your test now, because we only have a few minutes. Well, let's do things that hopefully you know. When is the test? What day?
Monday.
Monday. What time's the test going to be? At least the standard time. 11 till
1.
2 hours. 1. Right. So, being brought to my attention, and I understand this, that for some of you that just doesn't work. Right, your schedule interferes with your next class. For some of you, it doesn't work because you have access services that's giving you more time. So what you're going to do is, if that time schedule doesn't work, then you're going to shoot me an email and you're going to tell me the times that you are free, and we will arrange a different time slot for you. For instance, I have a time slot that goes from 7 till 9. Maybe you don't have a morning class and that'll work for you. So you send me an email and tell me when it's going to be free, and I will arrange the test to try and accommodate you. Now, once the test is over, it's just like test 1. You've got half an hour to do it onto Canvas, right? Upload your working. During this time, the normal time, for want of a better word, of the test, there will be a Zoom meeting, so I can see that you're not cheating and you can ask me help. Right. The test is on what chapter?
6.
And only 6, right? And it's going to start, your first question is going to be from 6.1, and the last question is going to be about pulling ropes up buildings, right? So I always do my test chronologically. What else do I need to say? Homework is Sunday, so make sure you get the homework done by the end of Sunday midnight. I think I've covered everything.